All right, we are going to start chapter 4. So we are specifically going to be looking at polynomials, their graphs, and a bunch of other stuff with them. So let's go ahead and define what a polynomial is. So it's a function of the form p of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot dot dot. So it's following that pattern all the way down to we get to a sub 1 times x plus a sub 0. All right. Welcome to PreCalculus. So we're going to start looking more and more like of these things where it's a bit more technical because calculus is very technical and very formal. Okay, so this is the structure of a polynomial where every coefficient, so all of these a's, every coefficient is real, so a real number, and every exponent is a non-negative integer. So the exponents can't be negative, they can't be zero, they can't be a fraction, just positive whole numbers. All right, example 1, determine which functions are polynomials. For those that are, state the degree. So wait, what on earth is a degree? Well, that would be the highest exponent in the polynomial itself. And then for those that are not, justify your reasoning. So why is it not a polynomial? Explain yourself. Okay, part A, 5x squared minus 1/2 x to the 4th. Well, that pretty much fits the definition. Coefficients are real, exponents are all non-negative integers. So that is a polynomial, so yes. And the degree is 4 since that's the biggest exponent. Part B, that is also a polynomial that fits the definition. And its degree would be 2, because if I actually multiply that out, that would be x squared minus x, the highest power is a 2. Okay, example C, if I multiply this out, I get x minus root x. Oh, that doesn't follow the definition, so that is not a polynomial. And the reason being is that not all of your exponents are integers. This one it is, but on the square root of x, that is not. Okay, part D, this would be another yes. And the degree, well, if you expanded this out, that would be an x to the 3rd plus whatever. Well, an x to the 3rd times an x squared is x to the 5th. And that's the highest power. So the degree is 5. This one here, example E, that is a no, it's not a polynomial. And for the same reason, not all your exponents are integers. Because if you separated it, that would be x to the negative 1st minus 5x to the negative 3rd. You can't have negative exponents. Okay, so let's look at what we can put here in the box. So these are the most basic polynomials, just x to the n. So no other terms with them. So the first one is when n is even. It's like x squared, x to the 4th, x to the 10th, x to the 38th. If it's an even exponent, then its graph is going to be some sort of a parabola. So it's symmetric about the y-axis, and as n increases, so as the exponent gets bigger and bigger and bigger, the graph gets thinner. So if we were going to graph like x squared versus x to the fourth, x to the fourth would be pretty much contained within that parabola. So as the exponent gets thinner and thinner, or bigger and bigger, the graph gets thinner and thinner and thinner. Now if the exponent is odd, like x to the third, x to the fifth, x to the 101, that's where it's going to slide. So these would be symmetric. About the origin. And as n increases, the graph gets thinner. So it does the same type of thing as these. So like x, if this was x to the third, x to the fifth would do something like that, x to the seventh, like that. So if it was like x to the 101, it would look like it's almost straight vertical line, but it still has, you know, just a really slight curve to it. Okay. So when you graph these things, it's the same rules as it did if if it was like x squared, because we just changed the exponent, so it's not going to change your techniques. So how it moves up, down, left, and right, that's all still the same. Okay, so this, we're going to move it to the left because that's what makes this 0 by 2, and down by 3. So it's going to look like that. And if you set this thing equal to 0 and solve for x, you're going to come out with some crazy exponents, or answers, but that's okay. -2 minus the 4th root of 3. And that is the -2 plus the 4th root of 3. And then your y-intercept, this is so not to scale. Plug in 0 for x, and it ends up with 13. So that's what I mean. Like, please try not to do your graphs to scale, especially with these, because otherwise you're just going to drive yourself crazy. And you're going to drive me crazy too, because they're a little interesting to grade. All right, this one, it's got an odd exponent, so it's going to look like that, but we're going to move it around. So go to the right by 1, up by 2. So kind of like that. Okay, now how did I know that it was going to do just like this? Well, partly because of experience, because again, you got to make sure that you're putting your graph in the right spot, where in the right area for its intercepts. So when x is 1, or when x is 0, if you plug that in, that gives you the y-intercept, and it's going to be up here. If the y-intercept was negative, that means I'd have an x-intercept on this side instead over there. So I would have had to draw the graph accordingly. But I kind of cheated and knew what it was ahead of time. Okay, so that y-intercept is 3 over 2. If you set this equation equal to 0 and solve for x, that'll give you your x-intercept of 1 minus the 5th root of 4. All right, I'll stop the video here, and then we'll pick up in the next one and start talking about zeros and degrees and multiplicity and that sort of stuff.